Right. So I was saying that this makes sense, that the velocity would be zero when I am at rest. Why? Because velocity is the rate of change of displacement on time. What is displacement? It's the distance moved in a specific direction, right? So if I have a particle, let's just say this, let's just pretend it's a circle, and my particle is moving this way, it's moving, it's moving, it's moving. It has a velocity of 3 meters per second. And it's going to the right, so we're taking that as positive, positive 3 meters per second. Remember your sign. Why? Because velocity is a vector, so it has both magnitude, which would be the 3 meters per second, and then direction. This positive sign tells me that it's moving to the right. Okay? So that's my body moving. But then if I tell you it's at rest. If I am at rest, that means that I'm not moving. If I'm not moving, then I'm not traveling, right? Displacement, distance traveled in a specific direction. If I'm at rest, so I'm stationary, I'm in place, I am not moving any distance, right? So basically, my displacement would be zero. If I have zero, right, a zero displacement, hold on. Right. So let's just assume that my rate of change of displacement is zero. I substitute that into this formula, zero, and let's just say the time taken was 1 second. Zero divided by any number will give me zero. So if my distance is zero, my displacement is zero, velocity has to be zero, just mathematically speaking, right? So that's why we say velocity is zero. If my body or particle or object is at rest. What if I said, and I explained this one last time, the maximum velocity thing, and I drew a whole diagram and I said, if I'm at my maximum velocity, that means my velocity would never change. Let me just draw that again just in case you forgot. So this is my particle, I'm moving. So at this point, I realize that my particle is moving at a velocity of positive 3 meters per second. Then I check again the velocity at this point, and I realize it's also 3 meters per second. And then at this point, it's also positive 3 meters per second. So at each point I check the velocity of this. This is the same particle, right? Same particle. But at this point I check the velocity. At this point I check the velocity again of the same particle. Then at this point I check the velocity again. And I realize that at each point my velocity is the same. So the magnitude is the same, 3 meters per second, and the direction is also the same. At each point, the particle is still moving to the right. Oh my, hold on. I'm now seeing this. Wait, what's going on? Is velocity the rate of change? Oh wait, no. Okay. As you mentioned, A is equal to dV on dt, last class that is. Both of those nodes are denoted by a horizontal line on their respective graphs. You mean velocity, when the velocity is zero and acceleration is zero, if on the graph that would look like a horizontal line? Yeah. Yes, it would. Because the gradient of a horizontal line is zero. Yeah. Right. So I was saying, if this is the highest velocity I can have, so let's say a car, let's just say this particle, the highest possible velocity can go is 3 meters per second. It cannot go above that. It could go below that, yeah, but it cannot go above that. It cannot do 3.1, 3.00000000001. No, 3 is the highest, right? So that means at each point, I could continue forever. I would continue to get this, well, let's just assume that, it's continuing to travel at the maximum velocity. I would continue drawing these points and checking. And you would realize that it would never pass this velocity, right? So 3 meters per second, 3 meters per second, 3 meters per second, all of them still traveling to the right. If you go back to the definition, that's why it's important for you to know definitions, right? To understand them. If the definition of acceleration is the rate of change of velocity with respect to time, let's just say between this point and this point, it's 1 second. And then between this point and this point, it's also 1 second, right? Just so that's in a different color. I explained this one last time, but just in case. So it's 1 second, 1 second. If I want to find the acceleration between these 2 points, so it took me 1 second. Remember, A is the rate of change of velocity, V minus U on the time taken, right? V, which is my final velocity, would be 3. If I'm checking between these 2 points, it's 3, positive 3. And then U is also positive 3. T is 1 second. 3 minus 3 is 0. 0 divided by anything would give me 0. If I do the same thing here, it would be the same thing, right? So final is 3, initial is 3 divided by 1 second. It would give me back 0. Even if I decide to check the acceleration from here, this point, to this point. So let me do that, right? Final velocity is still 3. Initial velocity is still 3. But now the time taken from this point here to this third point would be 2 seconds. Because here to here is 1 and here to here is 1. So this total time taken would be 2 seconds. But notice my acceleration is still 0. Because 3 minus 3 is 0, and 0 divided by 2 would still give me 0. And that's why we say at the maximum velocity, acceleration is 0. So these are 2 important things you need to note, right? Okay, and we did the cross, displacement time, we finished that, distance time, we did that, velocity time and speed time. That's what we're doing now, right? So we said the key features of the displacement time graph. Displacement is on the y-axis, time is on the x. So this is d for displacement, t for time. If the gradient of the graph is velocity, we know that because the rate of change of displacement is velocity. So the gradient is velocity, and I explained that last class, right? So I won't waste time doing it again. Straight line, we said, is a constant velocity because we know that straight lines have a constant gradient, so it's constant velocity. If it's a curve, we know that the gradient of a curve is not the same at every point. That's why we say if it's a curve, so let me just say my graph looks like this. I know because this is a curve, the gradients are different. And if the gradients are different, that means that my velocities will be different. That's why we say varying velocities, meaning that it's not the same. Horizontal line, it means that the object is stationary or at rest because we're not moving. I explained that last time, right? And we did this question, just to make sure you understand what's going on. And the last thing I did was distance time graph. So slightly different from displacement time graph. Distance would be on the y-axis, time would be on the x. The gradient isn't velocity now, but like I said, you might hear some teachers saying it or even read it in textbooks. They would use, okay, let me draw this out. So let's say this is my displacement time graph, and this is in TIST for displacement, T for time, versus distance time graph. We know displacement on time, that's velocity, and distance on time is speed. But some teachers or some textbooks may use the meaning of the gradients interchangeably. So they might say, okay, this is a displacement time graph. I know that the gradient is velocity. But then they would look at this distance time graph as well and say the gradient is velocity, which technically isn't the correct thing to say, but it is done, right? People do that. Anyways, they do that. So don't be frightened if you see that anywhere, right? A straight line, once again, shows that we're moving at constant speed. Because a straight line has a constant gradient, if my gradient is speed, that means I have a constant speed. Hold on, let me check the chat. Right. When doing a curve, we use derivative gradient function. Yes. Hold on, let me just read that for anybody who's watching this recording later on. When doing a curve, we use derivative gradient function of the function of the curve at the point of tangency, right? Yes, we do. That's how you find the gradient at that point. We draw a tangent to that point and find the gradient of the tangent. Yeah. A curve shows that the body is moving with varying speed, just like before. Horizontal line means that the object is stationary or at rest. Like I said, it's very similar to the displacement time graph, only now it's speed instead of velocity. And there's one other thing you need to note. Distance time graphs cannot go below the x-axis, but displacement time graphs can. And last class, I was explaining that we say this because displacement is a vector quantity, meaning that it has both magnitude and direction. So let me do distances from a point A to a point B. That's the example I gave last time. I might tell you that the distance from A to B is 5 meters. This is a magnitude. The 5 meters is a magnitude, and that's called distance. Distance is a scalar quantity, it only has magnitude, right? So from A to B, the distance is 5 meters. Cool. I can only have positive values for my distance because there's no direction, it's only magnitude. So we really only taking the positive value. So I could only take positive values. Okay. That's why it always stays within this region. Plus, you know, time can't be negative, right? So we only using the positive x-axis. But for distance time graphs, we have to use the positive y values only because distance is a scalar quantity. It does not have direction, therefore I cannot have a negative distance, right? But displacement, hold on. Displacement is a vector quantity. It's distance traveled in a specific direction indicating that there's direction. It's a vector quantity, right? Magnitude and direction. So yeah, this is the distance between A and B, 5 meters. But if I tell you, yeah, again, I have a particle. I'm not sure it is this way. Let me say my particle is moving from B to A. So going to the right, which is A to B, let's say that's a positive direction, and going to the left, B to A is negative, right? So yes, the distance is 5 meters, but the displacement would be negative 5 meters. That minus sign, all that tells me is that instead of moving to the right from A to B, I'm moving to the left, B to A. Notice this is a negative number. And that's why our displacement graph can actually go all the way down here into the negative. It can have negative y values. And like I said, we know t is a scalar quantity. You can't have a negative time. So it would always be the x-axis, the positive x-axis that we're using. But for displacement time graphs, displacement is a vector quantity. So I can have positive values for my displacement, or I could have negative values for my displacement. Do you remember that? No, displacement is in meters per second. Displacement is in meters. Just like here. Just in case you don't understand that, you told me V is the rate of change of displacement. Let's just say S is my displacement, right? Can you tell me? So that means, yes, velocity is meters per second. That's what I was going to show you. Meters per second is the unit for velocity. If I said that the unit for displacement is meters per second, then I said the unit for time is seconds, that wouldn't add up. It would be meters per second squared. But that's not the unit for velocity. The unit for velocity is meters per second. So that's not right. The unit for displacement is actually meters. And that's how you would end up with the meters per second for velocity. That would, oh no, we don't write it like that. Acceleration has the unit meters per second squared, and we actually write it like this, meters per second squared, or you could write it as meters minus b. Yeah, this or this, it's correct either way. And that's the, yes, it is a physics thing. Kinematics is a physics topic. Right, so yes, that's the unit for acceleration, right? Just in case anybody did not remember that. I did most of this in physics. Yes, it's actually a topic in physics. I actually started off saying that when I started this. So let's move on to velocity time graphs now. What are the key features that you need to know? Well, velocity, which look unit meters per second, or like I just showed you, you can write it like this. Either way, either one is correct, right? Meters per second. It's on the y-axis. So let me use v meters per second. And then, of course, t is still on the time, right? On the x-axis, because it's a velocity time graph. So t is still on the x-axis. The gradient is acceleration. So let me just explain this real quick. Very similar to the other one. Let's say I have a straight line going through the origin. We know to find the gradient of a straight line, we would use the formula m is equal to y2 minus, a trick is whatever is stated first on the one. Yes, that's actually a physics thing, because you might see in physics, plot a graph of velocity versus time. Because velocity came first, you know velocity is on the y-axis. So m, which is gradient, is y2 minus y1 on x2 minus x1. Or some people say the change in the y values over the change in the x values, or rise over run, whatever helps you remember, right? Once you're doing the right thing. That's all that's important. So we know, especially for my physics people, you want to find the gradient of a line, you take 2 points on the line far apart from each other. And people doing math too, right? Because you have to draw graphs in math. So if I want my x value of this point, I'll draw a line down here, check the x value, check the y value. That's my y1 and x1, because that's the smaller, values, right? This would be x2. Let's just pretend you can see the 2 there. And this would be y2. So notice all my y values, so y1, y2, they are on the y-axis. Of course, that's why it's called y1 and y2, right? And for this particular graph, the quantity that's on the y-axis, it's velocity, right? Just some people, this right here, m, can actually be written as the change in the y values. So that triangle is called a delta sign, physics people. Delta meaning change. So change in my y values divided by change in my x values. And change just means to subtract them, just like this, right? The bigger number minus the smaller number. So physics people, this should be familiar to you. Delta y divided by delta x, meaning the change in my y values, which is y2 minus y1, divided by the change in my x values, x2 minus x1. Notice for this particular graph, velocity time, my y values, the quantity on the y-axis is velocity. So my gradient, which is m, is actually the change in velocity divided by the change in x, delta x, the quantity on the x-axis is time. So instead of writing delta x, I can write delta t because t is on my x-axis. T is my x values, right? Time. From your differentiation, you would know that when I say change of something or rate of change of something, I can actually represent this as dv on dt. Everybody following this so far before I continue? Independent variable is a time after x velocity. So I came up with a bold conclusion: acceleration, rate of change of velocity. Acceleration is the rate of change of velocity. Yes, it's like, oh, I guess. Let me just go back to the definition real quick. That's why it's important for you to know this, right? Acceleration is the rate of change of velocity. Let me use a different color. Acceleration is the rate of change of velocity. When we were doing rates, that's why I did it before we did this. Rates, when I say rates, I mean with respect to time. So whatever it is on dt. In this case, it's a change of velocity. So that's dv on dt. dv on dt is acceleration. Back to what we were doing. Wait, I'm too far. Back to what we were doing. dv on dt, rate of change of velocity, is acceleration. And that's why we say the gradient of this graph is actually acceleration. Wait, really? It's about to end? Oh, okay, we have some time. Do you understand that? Do you understand how I got acceleration to be my velocity? I mean, my velocity gradient. Yes. Okay, I need everybody to answer me. The gibberish person, the person with the gibberish name. Tanya, Micaiah, Troy already answered. Yeah. Yes, is that a question? If you don't understand, please let me know. This is the time to ask me questions. That's not Russian. Anyways, if you understand how I got acceleration to be the gradient. Yes. Okay. Titania, do you understand? Okay. Micaiah, do you understand?
Yes, miss.
Nice. So I'm putting this now. Too many things on the screen at the same time. A curve, just like before. We know a curve, the gradient is not the same at every point. Therefore, since gradient is the since acceleration is a gradient of this graph, and the gradient of a curve changes, that means that I have a varying acceleration or a changing acceleration, or you might say an acceleration that's not constant, right? Similar to the two other graphs. Horizontal line means that the object is moving at a constant velocity. Let me draw this. Velocity, y, time, and the x. I said a horizontal line represents a constant velocity. Hold on, let me check the chat. Yeah. Right. So back to our definition of velocity. If you look at this graph, let's say my value is 3. If I check, let's say this is 1 second here, this is 3 seconds here, and this is 1 second. Just random times, right? If I want to check the velocity at each after this amount of time. So after 1 second, what's my velocity? After 3 seconds, what's my velocity? After 4 seconds, what's the velocity? That's what I want to find out, right? Well, from your graph, you would be like, okay, if I want to find the corresponding y value or the corresponding velocity at this point here, I would go up. Wherever I touch the graph, I would read off that y value, right? Which is 3 meters per second. So after 1 second, I found out I'm traveling 3 meters per second. Well, a velocity of 3 meters per second. What happens after 3 seconds? After 3 seconds, what's my velocity? I check again. I draw a line until I touch the graph, and then I read off the y value. So I realize after 3 seconds, so from my starting point, which is the origin, after 3 seconds, I check, and I realize I'm still traveling at 3 meters per second. Okay. I want to find out what's my velocity after 4 seconds of starting. So I started at the origin. What happens after 4 seconds? What's my velocity? So I check. Okay, the graph stops here. I touch the graph here. I read off the y value. After 4 seconds, I'm still traveling 3 meters per second. That's why we said it's a constant velocity. The velocity remains the same. Yep. So that means that the maximum v is 3 meters per second and the acceleration is 0. Well, yes, if I have a constant velocity and there's no change, remember acceleration is the rate of change of velocity. So if I have no change in velocity, then my acceleration is 0. So yes, that's correct.
Miss, no change in velocity, then the acceleration is what?
0.
Oh, oh yes.
Let me just write that out for anybody. V minus u on t. So acceleration is the rate of change of velocity. So we represent that as the final velocity minus the initial velocity on t. But from that whole gradient talk I did just now, we know that when I'm talking about the rate of change of velocity, I can actually represent that as A is delta V on delta t, to represent the rate or the change in velocity. But if at each point my velocity remains 3 seconds, 3 seconds, 3 meters per second, 3 meters per second, 3 meters per second, then I have no change in velocity because the value is still the same. And if you did not pick up on that, let's just say you substitute the values into here, 3 minus 3, it's going to give you 0. 0 divided by any number would give you 0. And that's why at a constant velocity, acceleration is 0. Do you understand now? Everybody? See, nice. Hey, Tanya, Troy, Kyle, what happened? Are you alive?
Yes, miss.
Katanya, right? Read the chat. Yes. The air, right? Very important. This question is probably gonna come. Like if you see velocity time graph, they're probably going to ask you for distance travel. Like, yeah. Make sure you know this. So the area under graph is, well, under this graph, velocity time graph, is actually the distance traveled. Yeah. So if, let's say, they gave you a graph just like this, and they ask you, so this is my graph, right? Velocity time graph. Let me just erase this. Erase this. They told you that you started at the origin, so right here at 0 seconds, and you go up to 4 seconds. And they ask you to find the distance traveled. So they gave you this graph. They told you You reach up to 4 seconds. And I ask you, what is the distance traveled throughout this whole thing? Well, in order to find that, you actually need to figure out this, the area, okay, this area.